Dimensions of the buckets. So to see the dimensions of the buckets, you have three-dimensional diagram here. So you can see this three-dimensional diagram. Now, if you draw its two views, that is, the top view is over here. This is the top view, and this is the side view. Okay. Now you can see these two views. Now in these two views, we have three important dimensions. One is B, another is capital T, another is H. Okay. Now this B is called the width of the bucket. So B is called width of the bucket. Now all these dimensions B, T, H, it depends on one dimension, that is D. Now this D is dia of the jet. This is diameter of jet. So this is the diameter of the jet which is striking at the splitter over here. This is small d. So all dimensions B, T and H depends on this diameter D. So B is the width of the bucket. So that is equal to 3 to 4 times the diameter of the jet. Then the next is T. Now this T is called thickness. This is thickness of the bucket. Okay, this is equal to 0.8 to 1.2 times D. This you can see in side view. Okay, this is 0.8 to 1.2 times the diameter of the jet. The next dimension is H. This H is called height of the bucket. Okay, this height is equal to 2.4 times, you can say 2.4 to 2.8 times the diameter of the jet. So that is in top view you have. So this is H, this is B, and this is T. So these are the three main important dimensions of a bucket: width of the bucket, thickness of the bucket, and height of the bucket. Then the other important dimensions for the bucket, that is, one is capital E. Okay, so this is capital E, you can see over here. So capital E is 1 to 2 times the diameter of the jet, that is E. Then F dimension, that is over here. So F is equal to 0.4 times diameter of the jet, that is F. Then G is equal to 0.8 to 1 times D, diameter of the jet, that is this one G. Okay, then we have two angles. One is called beta I. So beta I is the angle of splitter, and its value is 3 degree to 6 degrees, that is beta I. Then angle beta O, this is angle beta I. Then angle beta O, this angle beta O is 10 to 20 degrees. Now beta O is, you can draw over here. Now this is the horizontal line. Okay, and at this edge you can draw a tangent that give you angle beta O. Okay, so this angle is beta O. Okay, and this value is 10 to 20 degrees. It varies from 10 to 20 degrees. So these are the various dimensions of the bucket. The next is the number of the buckets. So for number of the buckets, we have some deciding factors. One is the frictional loss. The one factor is the friction loss. Okay. Now this loss, as we all know, must be on minimum side. This loss should be on minimum side. So this loss should be minimum if we have minimum number of buckets. Okay. So as the number of buckets increases, this friction loss increases. So this law says we should have minimum number of buckets on the runner. Now the another point that is the deciding factor to the number of buckets is now the water which is deflected, you can say the deflected water. So when jet strikes the bucket, the water is deflected. So that deflected water should not strike back at the incoming bucket. So that means again our requirement is the minimum number of buckets. Okay, if we have large number of buckets on the runner, then it happens that when jet strikes on a bucket, that deflected water from that bucket must strike on the next incoming bucket. So that is possible if we have large number of buckets. So to avoid that, we should have the minimum number of buckets on the runner. Okay. Now the another factor is the available jet must be fully utilized. Okay. So jet available with us, that should be fully utilized. So if we want to use that jet fully, so this factor says we should have maximum number of buckets. Okay, so these two factors says we should have minimum number of buckets. This factor says we have maximum number of buckets. So we must have some optimized number of the bucket on the runner. Okay, so that optimized number of bucket is given by one relation that is called Tygon's equation. Okay, now this equation says the number of buckets, that is capital Z, is equal to D divided by 2D plus 15, where D is the diameter of the runner, and small d is the jet diameter. Okay, so d divided by 2d plus 15 gives us the optimum number of buckets on the runner. Now further, we have one term m that is equal to capital D divided by small d. This is called jet ratio. This term is called jet ratio. So again, I can write z as equal to 0.5 m plus 15. So with the help of this relation, we can calculate the optimum number of buckets on the runner of a Pelton turbine. The next is the formula for diameter of the jet. Okay, so we know that velocity of jet that is coming out from the nozzle is given by CV under root of 2gh. Okay, so VI is the velocity of jet. Okay, VI is velocity of jet, or you can say this is the inlet velocity to bucket. Okay, so CV is coefficient of velocity. Okay, its value is 0.96 to 0.99. Okay, and H is the net head. H is the net head. So this is the formula for velocity of jet coming out from the nozzle. Okay, now further the discharge through the nozzle that I can write as Q is equal to cross sectional area pi by 4 d square into VI. Okay, now further I write it as pi by 4 d square into CV under root of 2gh. Okay, so this is equal to the discharge Q. So if you have the value of discharge, we have the value of H. So we can calculate D, that is the diameter of the jet. Okay, so with this you can calculate the diameter of the jet. The next is the formula for speed ratio. Now this speed ratio is noted by Ku. Okay. Now this is defined as the ratio of tangential velocity of a runner, that is u, to the velocity, that is the theoretical velocity, okay, theoretical velocity of jet. So theoretical velocity of jet is under root of 2g at, that is without cv. So I can write ku is equal to u divided by under root of 2gh. So this is the formula of speed ratio for Pelton turbine. Now you can note here one important point, that the value of ku, the maximum value of ku is 0.5 for maximum efficiency. Okay, so this we have uh, we are going to prove also in the next coming articles, that the value of ku is, the maximum value of ku is 0.5 for maximum efficiency. However, if we consider the nozzle friction, that means if we consider the value of cv, this value of ku is less than 0.5. So if we consider the friction of the nozzle, then the value of ku is approximately, or you can say in the range of 0.46 to 0.48. Okay, so this is the speed ratio. Then next is the jet ratio. Okay, so jet ratio is m, small m, and it is the ratio of dia of the runner to the jet diameter. So this is the runner diameter, and this is the jet diameter. Okay, now further, this ratio is a function of specific speed. This ratio is a function of specific speed. Okay, now the formula for specific speed is n under root of p h raised to power 5 by 4. So now I am going to prove that this specific speed is a function of jet ratio. So you can see now u, tangential velocity, that is equal to pi d n divided by 60. So from here I can calculate n as 60 u divided by pi d. Now further u is in term of speed ratio, I can write it as 60 into ku under root of 2gh divided by pi d. Okay, so this is the value of n I have. Then p, you can see power is given by w q h, okay, into overall efficiency, that is the power output. So this is in watt. Okay, so I can write it as, now w I can write as rho g into q. Now q I can write as discharge, that is pi by 4 d square into cv into under root of 2gh. Okay, this is q, w, then q, then I have h. Okay, then I have overall efficiency. Okay, now if I want to write this in kilowatt, so I have to multiply this by 10 raised to power minus 3. Then this term is in kilowatt. Okay, so this is the formula for p I have now. So I have p, I have n. So I put these two values in the formula of ns. So I have the relation ns is equal to 60 ku under root of 2gh divided by pi d h raised to power 5 by 4. Okay, under root rho pi by 4 d square CV under root of 2gh into g into h overall efficiency into 10 raised to power minus 3. This is all in under root. Okay. Now for a given turbine, if I say I have a turbine with overall efficiency, say 87%, so I use the term eta O as 0.87. Okay. The maximum value of Ku is say 0.46. Okay. Then CV is 0.98. So if for a turbine I use these values, so then I found the relation for NS. You can put all these values and then solve that. You see this is equal to 210 d divided by d. So this proves that specific speed is a function of jet ratio. You can say specific speed is a function of jet ratio. Okay. Then the number of jets. How we decide the number of jets? Okay. So now the discharge. So discharge is given by pi by 4 d square into Vi. Okay. So if I need more discharge, so that means there is more value of Vi and there is more value of D. Okay. So the purpose to increase the number of jet is to increase the discharge. So if I want to increase the discharge, that means I have to increase D as well as Vi. But when I proceed further, I see that the values of these two factors for a given value of head and discharge is limited. So we have given value of discharge available in the reservoir. We have fixed value of head. So depending upon these two factors, we have the fixed value of number of jets. So how you can see that? Now this Vi, now you can see this Vi is given by CV into under root of 2gh. So I have fixed value of h. So that means I have limited value of Vi. Okay. So now I see to increase the discharge, I have to increase D. Okay. Now further this D depends on jet ratio. Okay. Whose value is depending on or a function of specific speed. So for a given turbine, the specific speed is fixed. Okay. The specific speed is fixed. Now further you can see D. So I have U pi d n divided by 60, or in term of speed ratio, if I write U, that is Ku under root of 2gh. So you can see for fixed value of h, my U is fixed or limited. That means U is equal to pi d n by 60. So that means I have fixed value of d. So as my specific speed is limited, ns is limited, d is limited. So that means I have a limited value of d. Okay. So I have now reached one conclusion that I have a limited value of d and vi. Okay. So I cannot increase q beyond a particular limit. Okay. So the number of nozzles I cannot increase from a particular value. That does not solve my purpose to increase the value of Q to the turbine. This is because of the limiting value of these two factors. Okay. So to use the available discharge at maximum optimum level, I can use the number of nozzles up to 6. So the maximum number of nozzles or you can say jets, that uh, is up to 6. Okay. Now you can see in this diagram how I can use the nozzles. So in this diagram, you can see I have two nozzles. So here one nozzle and here is the second nozzle. Okay, now you can see the another diagram. Okay, so in this diagram, you can see I have four nozzles. One, two, three, and four. So like this, the maximum number of nozzles that I have in the Pelton turbine is up to 6. So if I try to increase this number beyond 6, then this whole system becomes complicated